All right, perfect. Cool. So hi, everybody. Welcome back to the Graduate Online Combinatorics Colloquium. Today, we are very excited to have a wonderful speaker here. Before we start, I want to remind everybody of our community statements, which are the guiding principles that we have here. Those are that we are all learning, everyone has something to contribute, and no one has all the answers. So we are thrilled to have with us today Etienne Totrell, who's going to talk about plethystic decomposition of power symmetric functions. So go ahead and take it away.
Hi, so thank you for inviting me. So today I'll talk to you, like the title, the plethystic decomposition of power symmetric functions. So it is, so I will talk about an operation on symmetric function, which is called plethism. So first of all, why do we study plethism? So where does it come from, this operation? Well, turns out that it comes from the representation theory of the general linear groups. So if we take this theory, a representation corresponds to a symmetric function via the character type. So I won't go into details of representation theory, but you can think a representation corresponds to symmetric function. Now, the irreducible representation, because GLN can decompose all their representation into irreducible, and the irreducible correspond via the character to the Schur function, which I'll define later on. And we can compose representation of GLN, and their composition, the character, is the plethism. So plethism really comes from representation theory of the general linear. So a problem in representation theory is to write a composition of representation into irreducible. That's a hard problem in general. It's not solved yet, except for really small cases. So, but we will work in the world of symmetric functions. So what our goal today will be to write a plethism in terms of Schur function, which is an equivalent problem. So that's the origin of the problem. Now let's start with the symmetric function theory. So some preliminary notions. So first, a partition. Well, it's a sequence of integers, which is weakly decreasing and strictly positive. And if the sum of all the parts of a partition is n, well, we say that lambda is a partition of n denoted by this symbol here. So for example, 4, 3, 1, 1 is a partition of 9, because the sum 4 plus 3 plus 1 plus 1 is 9. And we represent a partition by a diagram. And here I use the French notation, meaning that the biggest part is at the bottom. So if we are 4 cell, 3 cell, 1 cell, 1 cell to represent our partition. Now, a Young tableau is simply a filling of the diagram of lambda with positive integers. So for example, this is a Young tableau. We say that the shape is the underlying diagram. So here the shape is 4, 3, 1, 1, which is the diagram. We also need to use what we call the content. So the content is the tuple where nu I is the number of I in the tableau. So in this example, the content of our tableau is 3, 2, 2, 2, because there are 3, 1, 2, 2s, 2, 3s, and 2, 4. We also say that the tableau is semi-standard if the rows are weakly increasing and the columns are strictly increasing. So in this example, it is a semi-standard Young tableau. And we denote by SSYT of lambda nu to say the set of semi-standard Young tableau of shape lambda and content nu. Now, using this, we can define the two symmetric functions that we will use in this talk. So first, denote by bold x to be an infinite set of variables. A Schur function S lambda is the sum over all semi-standard Young tableau of shape lambda and of any content. So when I write a little bar like this is to say any. And each monomial corresponding to a tableau is simply the x to the content of t, meaning that x to the I, its exponent, is the number of I in the tableau. We also have to define the homogeneous symmetric function. So when it's only a number, Hn is equal to Sn, so the partition with only one part. And we can also think of Hn as the sum over all monomials of degree n. And for partition, we denote h lambda to be the product of h lambda 1 through up to h lambda k. And what we have to notice is that both the Schur function and the homogeneous symmetric functions are bases of the space of symmetric functions. Now, to multiply a Schur function with an homogeneous symmetric function, we have what we call the Pierre rule. So the Pierre rule says that S lambda times Hn is the sum over all Schur function S nu, where nu is obtained from lambda by adding n cells, but no two in the same column. So for example, if we want to multiply S22 by H2, well, it corresponds to this sum because it's the three possible ways that we can add two cells to the diagram of 2,2, but no two in the same column. So we have that S22 times H2 is S42 plus S321 plus S22. Now, if we use this rule iteratively, we obtain, we can express an homogeneous symmetric function in terms of Schur function. So we have this rule here that H lambda corresponds to this sum here. So the coefficient of S nu is the number of semi-standard Young tableaux of shape nu and content lambda. So for example, if we take H222, which is H2 to the Q because of the multiplicativity of the homogeneous symmetric function, well, it corresponds to this sum of tableaux. So here we have all the tableaux which have content 222. So this means that H2 to the cube can be written as this sum of symmetric function because, for example, there's a coefficient 3 to S42 because there is 3 tableaux with have shape 42 and content 22. So here, why does it come from the Pierre rule? Well, you can think of the numbers as adding the new cells at each step. So the one represents the first cells that we add, the two the second times we add the cells, so that no two in the same column. So that's why semi-standard mean row are strictly increasing. And then we add the 3, 2. So it's really, we add the cells one at a time, and it gives us a semi-standard Young tableau. Now, it will be more useful to think of it as a sum over all semi-standard Young tableau of any shape, but of content lambda. And each Schur function indexed by t is given by the shape. So here we really want to think of H222 as this sum of tableaux. Well, the Schur function corresponding to this tableau, to these tableaux, but really we want to think of it as a sum of tableaux. So now we can define Plethysm and the types, which the types are our approach to understand Plethysm. So first, what is Plethysm? So I define where it comes from, but the definition. So let's take f and j two symmetric function. So their Plethysm is denote f bracket j, and we can really think of it as a monomial substitution. So often they are described by obscure rules, but when we have nice enough symmetric function, like in our case, we can define it as a monomial substitution. So what I mean by that is that if we take H2, which is the sum over all monomials of degree 2, so the power of each variable and the product of each two different variables, then if we want to know what is S21 of H2, well, we evaluate S21, but instead of evaluating it in each variable x1, x2, x3, x4, and so on, we evaluate it in the monomials that appears in H2. So we substitute the variables by the monomials of the inner function here. So obviously it's not commutative because of this property. So that will be important. But yeah, for nice enough symmetric function, we can define Plethysm this way. So here, if we compute, we obtain that this Plethysm is equal to this sum of Schur functions, S51 plus S42 plus S321. So why it is the case? Well, that's why we are trying to figure out. But So this one we understand. We will come back to it later on, but that's the hard part. How to write a Plethysm in terms of Schur function. So that's an open problem. So our problem is to write a Plethysm of a Schur function and an homogeneous symmetric function in the Schur basis. Often this problem is described, well, we want a Plethysm of two Schur functions, but in our case here, we are interested where the inner Schur function, when the inner symmetric function is homogeneous. So it's another basis, so it's also interesting, and we have more results using this approach. But there's very few cases that are known. It's really a hard problem in general. So our approach to understand this is to use what we call the Plethystic decomposition. So to state what is the Plethystic decomposition, we first have to define the standard Young tableau with M cells, which I'll denote by like this, SYT of M, which is really the standard Young tableau with M cell. And a standard tableau is simply a semi-standard Young tableau where each number appears exactly one time. So each number from 1 to M appears one. So for example, the set of standard Young tableau with 3 cells are these 4 diagrams. The only 4 tableaux that we can construct with a 1, a 2, and a 3. That being said, we can define the Plethystic decomposition. So the mth power of a symmetric function can be decomposed as a sum of Plethysms. So there's one Plethysm per standard Young tableau with M cells. And the inner symmetric function is always F, the one that we take the power. And the other is given by the shape of the standard Young tableau. So for example, the cube of a symmetric function can be written as S3 of F because there's only one tableau, a standard tableau of shape 3, plus 2 times S21 of F because there's 2 standard Young tableau of shape 21, and plus S11 of F because of this standard Young tableau. So, yeah.
Yeah, I have a quick question. So, so far, our Plethysms have ended up being adding what appears to be our terms. Is that, do we expect that, or should generally pluses and minuses signs be showing up?
Well, because it comes from a representation theory, all symmetric function we consider here come from representation theory, so they can all be expanded as a positive terms of Schur function. If we take other symmetric function that doesn't come from representation theory, they could be minus sign, but here all is positive, so you don't have to care about the sign.
Excellent, thank you.
Okay. So now, how do we want to use this Plethystic decomposition? It doesn't seem to help us, but it does. So we define types to define types, first notice that the m power of Hn, well, using the Pierre rule, Hn to the m is only H indexed by the partition n repeated m times. So by the rule we stated before, it's the sum over all Schur function, each one indexed by a semi-standard Young tableau of content n to the n. So there's n1s, n2s, up to nn in our tableau. But we also have the Plethystic decomposition in terms of Plethysm, each one given by a standard Young tableau. So this means that there should be a way to attribute to each tableau here what we call a type, so that the Schur function indexed by this tableau appears in the Plethysm that we want. So we say that a semi-standard Young tableau of content n to the m has type small t, where small t is a standard Young tableau, when we can write the Plethysm indexed by small t as the sum over all Schur function indexed by tableau having this type. So really what we are doing, it's here we have well, we can think of each plethism as a partition of this set, and we want to know in which plethism each function go in. So for example, if we do the case m equal 2, well, there's one tableau per shape with at most 2 rows. So for example, if we have h3 to the cube, it's equal to this sub because we have these tableaux of content 3, 3. And there's only one tableau per shape, well, because the ones are forced to be there. And on the second row, they are forced to be 2s, because if not, there will be 2 times the same in the same column. So really, there's only one tableau per shape with 2 rows. And a null theorem, which dates back to Littlewood, who defined plethism. So what I'll say is as old as plethism itself, is that such a tableau as type 1, 2. So this type here is that if the second part is even, so here the second part is 0, here it's 2. So these 2 tableaux have this type, and they have the type 1, 2 as a column if the second part is odd. So here there's 1 cell in the second row, 3 cells in the second row, so they are of this type. In terms of plethism, what it means that the plethism S2 of H3 is equal to this sum, correspond to these 2 tableaux, and S11 of H3 correspond to this sum here, which correspond to these 2 tableaux. So really, the case m equal 2 is really easy. The results are really old. But we will use it to generalize and to our approach. So to generalize, we have to make up some rules to help us defining which type of each tableau. So our rules come from stability properties of plethism coefficient. So what are they? So stability properties on our weakly increasing sequences of plethism coefficient. So they are theorems that are known in many articles. So there's many, well, not that many, but there's a few stability properties that we can use to define. So to use the stability properties, we first need to define an operation on tableau. So we say that if we take 2 tableaux, T1 and T2, we define the operation here with a V, which is, well, we glue each row together and we reorder the row so that they are in increasing order. So for example, if we have these 2 tableaux here, well, their gluing is simply give us this tableau because, well, in the first row there are four ones because of the 2 ones here and the 2 ears. There are 2 2s because of the 2 here and the 2 here, and 1 3 because of the 3. And same thing with the second row, correspond to these 2 2s, these 2 3, and well, the 3 alone is this one here. It's really, we glue the tableau together and we reorder them. Now, that being said, we can state our rules to attribute types to tableau. So suppose that we have a tableau and that we know its type. So we have some tableau and we know what its type. So the first rule is that if we add all numbers that appears in the tableau to the first row and then reorder the row, well, it doesn't change the type. So the type is fixed by this operation. Our second rule is that if we add a column with all the numbers appearing in the tableau, then it conjugates the type. So the conjugate of a tableau is the reflection along the diagonal of the tableau, or you can think as the rows became the column of the other. So this tableau, its conjugate is this one, for example. Now, a third rule, which is not in our article, but that I found last week, and I find it pretty nice, is that if we add the next number, so here in our tableau, the maximal entry is m, and if we add all the m plus 1 to the first row of T, well, it corresponds to adding m plus 1 to the type in the first row. So let's make an example, prefer example, it's clearer. So suppose that we have this tableau, and I have not explained why yet, but suppose that it has the type. It does have, but for now I haven't explained, so just suppose it has. So the first rule says that if we add a 1, a 2, and a 3 in the first column, like this, so I've added a 1, a 2, and a 3, well, it stays the same type. If I add a column, so here I have added to this tableau a 1, a 2, and a 3 in the same column, well, the type is the conjugate. So here the conjugate, because, well, the row here becomes the column here, and the row here becomes the second column. And finally, the third rule says that, well, if we add all the 4s to the first row, so here we have H2, so there's 2 4 to add, well, it corresponds to add a 4 to the type here. So really adding all the 4s here, add 1 4 here. We also have a fourth rule, but which is not defined by the stability properties. So if we want to understand Hn to the m plus 1, well, it's only Hn to the m times Hn. So it's really the standard Young tableau of content n to the m to which we multiply Hn, but multiplying Hn, really, it's just adding the cells m plus 1. So the next cell, the next cells, we add them. So really, this sum is just the sum of semi-standard Young tableau of content n to the m plus 1. But really, what I want to say here is that the next case is obtained by adding the new cell over the tableau. And we can also make the same thing with the Plethysm, the Plethystic decomposition, I should say. So here we have Hn to the m times Hn, which correspond to, well, our Plethystic decomposition, to which we multiply to each Hn. And by using the properties of Plethysm, really, it comes from to multiplying H1 to our type here. But multiplying by H1 is simply adding a cell because of the Pierre rule. So our rule is that if we add n cells with m3 m plus 1 to our tableau, it corresponds to adding a cell m plus 1 to the type. So really, when we want to augment the exponent here, it's really, we see what it does to add the cells to our tableau, and it adds this cell to the type. So for example, if we have this tableau, well, we have already said it has type 1, 2, because there's an even number of 2s in the second row. Here's 0, but it's even. So that means that we have these 3 tableaux to which we have taken this tableau and added the 3s. So these 3 tableaux have either this type or this type. So these are the 2 types that we can obtain by taking 1, 2 and adding a cell 3. And here is the tableau of content 2 to the 3, to which we have added 2. So we can build our type recursively. So if we know the case m, we can construct the case m plus 1 by just understanding how adding the new cells change the type. But how to determine which one? Well, here, because of the rules that I have said, we can say that this one is forced to have this type, because we have add all the 3s to the first row, so it adds a 3 to the first row of the type. But in general, it's not that easy. The rules don't make all the cases, so we have to find a result, and the result we have find for the case m equals 3, so that's our result, is that if we take a semi-standard Young tableau and we suppose that it has only 2 rows, because if there's 3 rows, well, we are forced to have this to fill the 3 rows, and it's a column, and we have already seen that a column conjugate the type. So using the rule, we can restrict our study to the tableau with cells with only 2 points. And let kappa be the number of 2s in the second row. So we have this theorem here, which I won't go too much into details, but here we can say that if kappa is even, so the number of 2s in the second row is even, Well, it means that it's come from a tableau of this type, 1, 2. So we have to know when do we add the 3 here to the type or the 3 here. And yeah, for the column here, we have these two conditions. And if one of these two conditions fails, well, it is forced to be the other type. So here, the congruence here, it's modulo 4. It's my notation. It's not the classical one, but it's my notation that I use for modulo 4. So really, we only need, if we have a tableau, we only need to know what is the length of the second row and the number of 2's in the second row. So if kappa is odd, we have here, and a little remark, here it's the two opposite case. So here is two possible value for modulo 4, and here is the two other possible ways to be modulo 4. So that's our theorem. So we have a lot. Yeah, sorry. So what I wanted to say here is that there's already a theorem which states what is the coefficient of a certain Schur function in a Plethystic, but it didn't split the standard semi-standard Young tableau. It was only a number, a formula that gives a number. So our new approach is to split the semi-standard tableau into types. And we'll see later on why it is useful in our case, because you can say, well, it's not that useful, but we'll see later on why it is. So as an example, if we take h2 to the cube, which is this sum of Plethysm here, well, we have already seen that we have all these tableaux, which has content 2 to the 3. And using our theorem, we can split it into types. So here, h3 to the 2 is equal to s6 plus s42 plus s2 to 2. Here we have the types of the same shape, so they are forced to have tableau of the same shape inside. So our theorem allows us to do that, and we can see that the rules here apply. So here I have added a 1, a 2, and a 3 to this tableau, so it stays the same type. Here I've added a column to this one, so it gives the conjugate types, and so on. So really, it respects all our rules, and it respects, well, obviously, it respects the decomposition of each Plethystic. So that's for the case hn to the cube. Now we want to go further on, and we want to decompose h lambda to the n. So how do we do this? Well, there's two decompositions for h lambda to the n. So first, let's denote h lambda to, well, not h, just lambda to the m to be the partition where each part is repeated m times. So using this notation, we have that, well, h lambda to the m is the sum of our semi-standard Young tableau of content lambda to the m. But we can also decompose h lambda to the m as, well, it's a product of homogeneous symmetric function. So we can put the exponent on each of these homogeneous symmetric function. So we obtain a product of a sum of Schur function for each lambda I to the n. So meaning that if we reorganize all of this and all these equations, we have here a sum of Schur function of content lambda to the n, and here we have a sum of product of Schur function, where the product is indexed by T1 through Tk, and, well, each Schur function corresponds to such a tableau. So this means that, so the first step that we need to do is that we want to decompose a tableau as a tuple so that our Schur function here, we know in which product it comes from. So here we have a product, it will give us this sum, it's forced because it's an equality. And yeah, so we want to know for each Schur function from which product it's come from. So that's what, Florence, with whom I'm working, presented in spring. Well, exactly this approach. It was for the case h lambda to the squared, but the same approach is working here. So we'll make it through an example. So take lambda to be 2, 2, 1, so that the cube of lambda is 2, 2, 2, 2, 2, 2, 1, 1, 1. I repeat each part 3 times. And let's take this tableau, which has content lambda cube. So really, this tableau indexed a copy of S843, because it's the shape of our tableau, in the cube of H221. So to know from which product it comes from, well, we split our tableau. So the M3, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So we split our tableau and we obtain what we call skew tableau. So there missed a part here, but it's well defined. You can define it. They are skew tableau. Now we put the entries to be all from 1 to 3. So we diminish the entries so that our tableau all have content n to the 3. And then we apply what we call jeu de taquin. So jeu de taquin is a way to take a skew tableau and to rectify it, to make a straight tableau, a usual tableau. And how does it work? Well, we take inner cells and we want to move the cells so that it's always stays semi-standard. And the magical here is that in any way you do this, you always get the same tableau at the end. So it's a well-defined operation. We don't need to put an order on the cells of what we do. We always obtain the same tableau. So here, if we make the jeu de taquin here to each of these tableaux, well, we obtain a triple of straight tableau, each adding the, so here it has content 2, 2, 2, 2, 2, 2, and 1, 1. So it means that our tableau here appears in the, right here. So here it's S411, S51, and S21. So here it's this copy of S411 indexed by this tableau in H3 cube. Here also in H3, in H2 cube, sorry. And here in H1 cube, and this was a copy of S843 in H221 to the cube. And we have the equality here. This is equal to this product. So really, this Schur function comes from this product of 3 Schur functions. Now, how does it help for Plethysm? So how to use it for Plethystic type? Well, for each of these tableaux, we can attribute to them a type. That's what we have done earlier. They are tableau of content n to the 3, so that we can attribute to each of these tableaux a type. And then we want to knowing the 3 types of these tableaux, knowing the type of this tableau here. So how do we do this? Well, we use what we call a Kronecker map. So first, we can decompose we can Plethystically decompose H lambda to the m in 2 ways, as we have done before. So we can decompose the whole function, so H lambda to the m. Well, this sum here doesn't depend on the function, the Schur function here. So it's the same Plethystic decomposition. But we can also put the m on each of the part of H lambda. So we obtain here a product of sums of Plethysm. And if we write it in the good way, we obtain that a sum of product of Plethysm, and each product here can be indexed by a k-tuple of standard Young tableau with m cells. So really, we have this equality here, and there's many, many, many more terms to the right than here, because, well, it's the same set, but to the k, so it's bigger here. So that means that we can write each Plethysm to the left here as a sum of product of smaller Plethysm here. So our goal is to find a map which comes from the tuple here to only the tableau here, such that a Plethysm of a product can be written as a sum of product of Plethysm with smaller symmetric function inside. So for example, no, not the example yet, sorry. We have a result to construct the map is that if we take S mu of a product, we know how to write it as a sum of product of smaller symmetric functions. So here the coefficient that gives how many they are the Kronecker coefficient. But Kronecker coefficient, they are not known in general. It's also a hard problem to know the Kronecker coefficient as for the Plethysm coefficient. So they are not known in general, but for small values of m, well, we can compute them. So we can find a way. We don't have general rules to do that, well, because they are not known. But we can construct the map for small values. And if there are more than two functions inside that are multiplied, well, we just use this function recursively. So well, I show an example, it will be clearer, but we just use the map again and again. So for the map S22, well, we have this decomposition here. So S2 of a product of two functions is equal to this sum of product of Plethysm. S2 of F1 times S2 of F2 plus S1 F1 plus times S1. So this means that these two pairs of standard Young tableau with two cells have 1, 2 as an image. So really what we want to say with the Kronecker map is exactly that. That because we have this sum, we want to attribute to each of these pairs this tableau. For S11 of F1, F2, well, we have the two other pairs of tableau with two cells, and we give them the image 1, 2, the column here. Now for the case of Plethysm with 3, so with tableau with 3, well, the maps looks like this. Well, we think it looks like this because here there are choices. So the shape of each pair of the tableau is fixed. You cannot change it. But here we have tableaux that have two possible filling to be standard Young tableau. So here we have to make a choice. And we don't know yet which choice is the good one. We're more used to work with Plethysm than Kronecker coefficient. So we try to come up with rules, but even with our rules, why this pair is there instead of this one? Why don't, like, we could exchange them and all will work well too. So we don't know which choice is the good one, but we just have to make one and we have a map that will work in our case. So yeah, that will be nice. I don't know if it could be an approach to understand Kronecker coefficient. I'm not an expert in that, but yeah, we want to split our pairs of tableau into fours. And if we want to compute F24, so the map with the tableau with 4 cells, where it gives us 100 pairs to split into 10 sets. So we've been able to do that, but it's really complicated and there's many choices and we don't know which one are the good one or so so in our case, we will take this map because we'll need it. But for the others, it's more complicated and we will really like to come up with real rules that gives us the good ones. So now that we're having this map, let's take back our example. We had this tableau here, and we have said that this tableau comes from this pair here. So we have split our tableau into a triple of smaller tableaux. That's what we have done earlier. Now to each of these tableaux, we can attribute to them a type. We have these 3 types here. And now we can know what is the type of this bigger tableau by using our map F33. So we take our pair here and we apply to it here F33. So I said so here we have 3 instead of 2, and I have said, well, just use this recursively. So that means that the map F33 is equal to this map here. So we take the image of the first two, it will give us a tableau, and then we take the map for this result and the last one. So if we apply our map to these two tableaux, we obtain this tableau here, and now we compute for this pair, and it gives us this tableau here. So finally, we have that this tableau, we split them into parts, we attribute to each a type, then we compute the map F33, and it finally gives us this type. So in conclusion, we have that the type of this tableau here is this one, meaning in terms of symmetric function, that the copy of S843 indexed by this tableau in H221 to the cube appears in this Plethysm here, the Plethysm index by this standard Young tableau with 3 cells. So if we are able to compute both the decomposition of Hn to the n and find a Kronecker map for this case, we are able to do the case H lambda to the n. So yeah, so really we want to, so really the main part, the hard part here is to understand Hn to the m, and then the Kronecker map will, if we are able to compute it, we automatically get the case H lambda to the n. So finally, what are the results? So the previous result, well, as I said before, the case Hn to the q to the square dates back to Littlewood, defined Plethysm. So it's an old theorem. Now I said it too, but the coefficient the Plethysm of Hn with a partition of 3 to the left, we knew what are the coefficients in the Schur expansion. It didn't split into type, but we knew the coefficients in the Schur expansion. But using only the coefficient, we couldn't do the case H lambda to the m because we really need to attribute to each tableau a type. But to prove our result, we use these coefficients. And there's also a result for the square of S lambda, which is from Carré-Leclerc in 1995. So we try to use our approach with H lambda to make it to S lambda, but it's really rare, it's really hard, and it involves Littlewood with Richardson coefficient. So a third set of coefficient. Well, these ones are known, but it's not that easy to work. And now our result, well, that's what Florence presented here in spring. So we did the case H lambda to the m for m equal to. And I also wrote here the case E lambda to the m because there's a well-known involution and symmetric function. And if we know the decomposition of H lambda to the m, we automatically get the one of E lambda to the m. Now, what I presented to you is the case where m is equal to 3. So we needed to generalize all our ideas here, but we have been able. And what we want to do in the future, well, obviously the case m equal 4 will be interesting, but I start to look at it and it's really more involved to do, but we're trying. And also it will be really nice if we could do the case S lambda to the 3, because really that will be like the, let's say, it's really the cube of Schur function that we want at the end. But using H lambda, we think we can go to it, but we're still looking. So that's all I had to say. So thank you.
All right, let's thank our speaker and open it up for any questions.
I have a quick initial question because it's not a full question yet. Could you pull up the slide with the definition of the Kronecker coefficient again? I'm going to write something down. Great, thank you.
Yeah, so it's not really the definition, but well, it
Sure.
should be seen as a definition, but
And now I'm going to stare at this for a while you answer other questions.
So this comes from the fact that the up algebra, the symmetric function are up algebra, and it comes from this theory, but I don't know much about up algebra, so I don't know what's the link, but I know it comes from there.
Well, those are kind of magic words for me, so thank you for saying them.
Yeah, for me too. So.
Well, no, I study monoids.
All right, so I have a question, and it might just be something that I missed along the way. But could you remind me, how do we attribute a type to a tableau?
Well, that's the art part. So can I change
Oh, okay.
it? So yeah, so for the case n equal 3, that's how we do that. So that's our main theorem.
Gotcha.
But yeah, that's a really hard part of all this. So the case n equal 3, we've been able to do that because we have the formula for the Schur expansion of each Plethysm. But for the case n equal 4, we don't even have such a formula, so it will be hard to prove our result. But we're trying. There's something we can explain a Plethysm in terms of quasi-symmetric function, and we're trying to use that to do our proof. But it's not that easy because yeah, it's hard to go from quasi-symmetric function to symmetric function. We have to find a sign reversing involution, which is really not clear which one we have to do. So yeah.
Cool, thank you. Other questions? Mark, do you know what you want to ask yet?
I have 3/4 of a question now, which is, you said that finding like Kronecker coefficients aren't known. I'm wondering if you get a good description of these Plethysms for homogeneous functions, like how well can you use that to work backwards to the Kronecker coefficients? Because you can h lambda cubed is h lambda times h lambda squared, and so like you are using these Kronecker coefficients to go forwards, but if you find these patterns, how well can you use them to work backwards? Do you have enough degrees of freedom to isolate them, or are you always going to run into issues of like, I don't know which of these things are being clumped together? Like I know that the sum of these coefficients is this, but I can't pick out the coefficients.
Yeah, well, we always have choices to do. So what we know is like when S mu is some small cases, we are able to know what is fixed is the shape. So there's for these small cases here, if we ignore the numbers in the tableau, this is fixed. We have no choice. But it's the fact that putting numbers in them, so choosing which tableau is which, that seems, well, for me, which is not used to Kronecker coefficient, it seems like pretty arbitrary. So
okay,
because our rule, so what we said, go backward, yeah, we have that because 1, 2, we have this pair of tableau. Well, we have chosen that, well, we want to add 3s to this pair of tableau, but then this pair of tableau also appears in 1, 2. So we've added the 3s there, but why should it be this one instead of this one? It's not clear.
All right. Thank you.
Hi, Ken, very nice talk.
Thank you.
I have one question for the S lambda to the 3rd power. Are you planning to use ribbon tableau or 3 ribbon tableau? Because that's what Kareli Claire did for the for the
Well, we have tried like for 1 month to use tableau with ribbon tableau of well, the 3 ribbon tableau, and it doesn't seem to work. To work. We've tried many things, but there's no like for the Carré Leclerc. There's like a crystal-like bijection between Yamanouchi tableau and regular tableau, but this bijection, if it exists for a 3 ribbon tableau, it seems really mysterious. We haven't been able to define operation to transform it to like the head of the crystal.
yeah, thank you.
And we have a question in the chat. Have
Yes.
you tried counting how many semi-standard Young tableau of a given type there are, at least in the m=3 case?
The number, well, that's the chance formula. So the chance formula that I talked at the end, which was the formula that we use to prove our result. It has exactly count the number of semi-standard Young tableau of a given type of a given shape. But yeah, we wanted more than the number. We wanted like really which tableau is of each type. But this formula gives also the number of semi-standard Young tableau of a given type because, well, it gives only the number, so it gives exactly what you're looking for. Thank you.
I have a question.
Yeah.
It feels to me like this mapping types and so on, like you're decomposing weight spaces of the representation in some way. Does that somehow make sense?
Not that I know it comes from representation theory of GLN, but I'm not that used to it. But what I can say is that we try to do a crystal approach, so an approach like in weight space and all of this, and it's really it doesn't seem to work well. So we add like there's a new thing. I don't know at which point it's new, but there's a thing called perforated tableau, which allows us to describe a crystal for each semi-standard Young tableau this way. So I've tried to come up with a bijection using these types of crystals, but it's really not obvious how one should or could do that.
Okay, thank you. It's a very nice talk. Thank you.
Thank you.
All right, any more questions? All right, if not, let's thank our speaker one more time. And thank you all for being here, and we will see you next week.
Thank you.